Welcome back. For the last few episodes, the right-hand side of our equation has been 0. That 0 meant nothing was pushing on the system, and the solutions we found describe its natural, undriven behavior. Now we turn on a forcing term. The equation becomes a y double prime plus by prime plus cy equals g of x, where g of x is some external drive, a voltage, an applied force, a seasonal input. Here is the structure of the answer, and it is the most important idea in the episode. The full solution is the homogeneous solution plus a particular solution. We already know how to find the homogeneous part. It is the general solution of the equation with 0 on the right. What is new is the particular solution, yp, a single solution that answers the drive. Today we find that particular solution by guessing its form, which works beautifully whenever g of x is a polynomial, an exponential, or a sine or cosine. Let's see why guessing even works. Before we guess anything, let's see why the answer always splits as the homogeneous solution plus a particular solution. Write the equation abstractly as L of y equals g, where L is the differential operator that takes y to a y double prime plus by prime plus cy. The key fact is that L is linear. Now suppose Ip is any one solution of the driven equation, and y is any other solution. Then L of the difference, y minus yp, is g minus g, which is 0, so the difference is a homogeneous solution. Rearranged, that says every solution y equals a homogeneous solution plus our one particular solution. This is enormously useful. It means we do not need to find all solutions of the driven equation directly. We only need to find one, any single particular solution, and the homogeneous part, which we already know how to compute, supplies the rest. The two arbitrary constants you adjust to meet initial conditions live entirely in the homogeneous piece, never in yp. Why should guessing the answer ever work? Because of one special property shared by polynomials, exponentials, and sines and cosines, differentiating them keeps you inside the same family. Differentiate a polynomial and you get another polynomial. Differentiate e to the kx and you get k times e to the kx, the same exponential shape, just scaled. Differentiate a sine and you get a cosine. Differentiate that and you are back to a sine. The shapes recycle. Now look at the left side of our equation. It is built from y, its first derivative, and its second derivative. If you feed in a function of one of these special shapes, the whole left side comes out as a function of that same shape. So, to match a forcing term g of x of a given shape, the particular solution must have that same shape. The plan then is to write down a guess with the right shape but unknown coefficients, plug it in, and solve for the coefficients by matching both sides. The unknown coefficients are undetermined, hence the name of the method. Here is the guess table, the heart of the method. If the forcing term is a polynomial of degree n, guess a full general polynomial of degree n, with an unknown coefficient on every power down to the constant. If the forcing is an exponential e to the kx, guess a constant a times e to the kx. If it is a cosine or a sine of omega x, guess a cosine omega x plus b sine omega x. And this is important, include both the cosine and the sine even if only one of them appears in g, because differentiation mixes them. For products, multiply the forms. A polynomial times an exponential gets a general polynomial times that exponential. 2 habits to build. First, always carry the full polynomial of the right degree, not just the top term, because the lower derivatives generate the lower powers. Second, if the forcing is a sum of several pieces, guess for each piece separately and add the results. That is just superposition. Get the form right and the rest is algebra. Here is the table as a picture. On the left are the 3 basic forcing shapes. A polynomial, drawn as a parabola, an exponential, drawn as a rising curve, and an oscillation, drawn as a wave. Each one flows across a gold arrow to its matching guess on the right. The polynomial maps to a general polynomial of the same degree with unknown coefficients on every term. The exponential maps to a single unknown constant times that very same exponential, and the wave maps to a combination of cosine and sine, both present, with 2 unknown coefficients. The whole picture says one thing: the guess is a mirror of the drive. Whatever shape is pushing on the system, the particular response has the same shape, and all that is left to discover is how big each piece is. Those sizes are the undetermined coefficients, and we find them by substitution. Let's do a polynomial example. Solve y double prime minus 3y prime plus 2y equals 4x squared. The forcing is a degree 2 polynomial, so we guess a full quadratic, yp equals ax squared plus bx plus c. Notice we include the linear and constant terms even though the right side only has an x squared, because the derivatives will generate them. Compute the derivatives. Yp prime is 2ax plus b, and yp double prime is 2a. Substitute all 3 into the equation. Now collect by powers of x. The x squared coefficient is 2a, the x coefficient is negative 6a plus 2b, and the constant is 2a minus 3b plus 2c. Match these to the right side, which is 4x squared with no x term and no constant. So 2a equals 4, giving a equals 2. Then negative 6a plus 2b equals 0 gives b equals 6, and the constant equation gives c equals 7, so the particular solution is 2x squared plus 6x plus 7. Pure algebra, no integration. Two quick ones to drill the other shapes. Part A, solve y double prime plus y equals 3e to the 2x. The forcing is an exponential, so guess yp equals a times e to the 2x. The second derivative brings down a factor of 4, so substituting gives 4ae to the 2x plus ae to the 2x equals 3e to the 2x. That means 5a equals 3, so a is 3/5, and the particular solution is 3/5 times e to the 2x. Part B, solve y double prime plus y equals sine x. Even though the forcing is only a sine, we guess both. A cosine x plus b sine x. Compute the derivatives, substitute, and collect the cosine terms and sine terms separately. Matching, the cosine side forces b equals 0 and the sine side forces a equals negative 1, so the particular solution is negative cosine x. Notice the answer is a pure cosine even though we were driven by a sine. That phase shift is exactly why you must include both from the start. One more habit before the trap, handling a forcing term that is a sum of several pieces. The superposition principle says that if yp1 solves the equation with forcing g1 and yp2 solves it with forcing g2, then their sum solves the equation forced by g1 plus g2. So you simply split the forcing, find a particular solution for each piece, and add. Here is a small example that also sneaks in the overlap idea. Solve y double prime minus y prime equals 2x plus 5. The forcing is a degree 1 polynomial, so you would normally guess ax plus b. But watch. The characteristic equation r squared minus r equals 0 has r equals 0 as a root, which means a constant is already a homogeneous solution. So the polynomial guess overlaps, and we bump it by one factor of x, guessing ax squared plus bx. Substituting and matching gives a equals negative 1 and b equals negative 7, so the particular solution is negative x squared minus 7x. The lesson, split the forcing and check every piece for an overlap. Now the famous trap, and you will hit it constantly, so watch carefully. Solve y double prime minus y equals e to the x. First, the homogeneous part, the characteristic equation is r squared minus 1 equals 0, with roots plus and minus 1, so the homogeneous solution is c1e to the x plus c2e to the negative x. Following the table, you would guess yp equals ae to the x. But substitute it. The second derivative gives ae to the x, and subtracting y, which is also ae to the x, gives 0. The whole left side collapses to 0, which can never equal e to the x. No value of a works. What went wrong? The guess e to the x is already a homogeneous solution. The operator was built precisely to send it to 0, so it annihilates our guess before any coefficient gets a chance. Whenever your guess overlaps the homogeneous solution, the plane table fails. We need a modified guess that survives the operator. Here is the fix, and it is wonderfully simple. Multiply the offending guess by x. If a piece of your guess is already a homogeneous solution, bump it up by one factor of x, and if it still overlaps, which happens when the matching root was a repeated root, multiply by x squared instead. Let's repair our example. Solve y double prime minus y equals e to the x, but now guess yp equals ax times e to the x. Differentiate with the product rule. The first derivative is ae to the x times the quantity 1 plus x, and the second derivative is ae to the x times the quantity 2 plus x. Substitute into y double prime minus y, the x terms cancel, and you are left with 2ae to the x. Set that equal to e to the x, so 2a equals 1 and a is 1/2. The particular solution is 1/2 x times e to the x. The extra factor of x lifted the guess out of the homogeneous family and let it survive the operator. Same idea, by the way, as the repeated root x we met last episode. Here is a way to see the modification rule geometrically. Picture a shaded region that holds all the homogeneous solutions. The functions the operator sends straight to 0. Our first guess, e to the x, lands right inside that region, so the operator kills it and it cannot match anything. That is the dead end. Now, the bumped guess, x times e to the x, lands just outside the shaded region. The operator no longer sends it to 0, it sends it to something proportional to e to the x, which is exactly the shape we need to match the forcing. The single factor of x was just enough to push the guess out of the operator's null space and into territory where it can do work. If the root had been repeated, the region would be thicker in that direction, and we would need x squared to escape. That is the whole logic of the rule. Keep multiplying by x until your guess clears the homogeneous solutions. Let's combine everything in one example that also previews resonance. Solve y double prime plus 4y equals sine 2x. First, the homogeneous part, r squared plus 4 equals 0, gives r equals plus or minus 2i, so the homogeneous solution is c1 cosine 2x plus c2 sine 2x. Now look at the forcing, sine 2x. The natural guess would be a cosine 2x plus b sine 2x. But that is exactly the homogeneous solution. We have an overlap, so by the modification rule we multiply by x, guess yp equals x times the quantity a cosine 2x plus b sine 2x. Substituting and matching coefficients, you find a is -1/4 and b is 0. So the particular solution is -1/4 x cosine 2x. The full solution is the homogeneous part plus that. And notice what the factor of x does physically. It makes the response grow without bound as x increases. That growing amplitude when you drive a system at its own natural frequency is resonance, the star of a later episode. Let's do one harder example that stacks a product forcing term on top of a repeated root, so we use the x squared bump. Solve y double prime minus 2y prime plus y equals x times e to the x. The homogeneous part first, the characteristic equation is r minus 1, quantity squared, so r equals 1 is a repeated root, and the homogeneous solution is the quantity c1 plus c2x times e to the x. Now the forcing is x times e to the x. The base guess would be a linear polynomial times e to the x, that is, the quantity ax plus b times e to the x. But look, both e to the x and x times e to the x are already homogeneous solutions, because the root is repeated. A single factor of x is not enough to clear them, we need x squared. So the guess becomes x squared times the quantity ax plus b times e to the x. Substitute match coefficients, and you find a is 1/6 and b is 0. The particular solution is 1/6 x cubed times e to the x. When the overlap is with a repeated root, multiply by x squared. A little history and a peek ahead. The idea of finding particular solutions for forced linear equations goes back to the 18th century work of Euler and Lagrange, who studied these equations as they arose in mechanics and astronomy. In the late 1800s, the British engineer Oliver Heaviside introduced his operational calculus, in which the derivative is treated as an algebraic symbol, capital D, that you can manipulate like a number. That viewpoint turned guess and match into honest algebra. It eventually matured into the annihilator method. You find a differential operator that kills the forcing term g of x, apply it to the whole equation, and the correct form of the guess, including exactly the right factors of x in the overlap cases, falls out automatically with no guessing at all. So the friendly table you learned today is really the surface of a deeper and very elegant operator algebra. Let's recap. The full solution of a driven equation is the homogeneous solution plus one particular solution, and the method of undetermined coefficients finds that particular solution by guessing its form. It applies whenever the forcing term is a polynomial, an exponential, a sine or cosine, or a product of those. Anything whose shape survives differentiation. Use the guess table to mirror the shape of the forcing, remembering to carry a full polynomial of the right degree and to include both cosine and sine. Substitute the guess into the equation and match coefficients to solve for the unknowns. Watch for the trap. If your guess is already a homogeneous solution, it collapses to 0, and you fix it by multiplying by x, or by x squared if the offending root was repeated. And for a sum of forcing terms, handle each piece separately and add by superposition. Next episode, the universal method that needs no lucky guess, variation of parameters, which conquers any forcing term at all. Today we learned to find a particular solution by guessing its form. The full solution of a driven equation is the homogeneous solution plus one particular solution, y equals yh plus yp. The method of undetermined coefficients finds the particular solution yp whenever the forcing term is a polynomial, an exponential, a sine or cosine, or a product of those. The reason it works is that each of those functions keeps its shape when you differentiate it, so the particular solution must share that shape. You write a guess with unknown coefficients matching the forcing term, a general polynomial of the same degree, a constant times an exponential, or a combination of cosine and sine even if only one of them appears. Then you substitute the guess into the equation and match coefficients to solve for the unknowns. There is one trap. If your guess is already a homogeneous solution, it produces 0 and cannot match the forcing, so you fix it by multiplying the whole guess by x, or by x squared if you hit a repeated root. That is the modification rule. Next episode, we build variation of parameters, the universal method that handles any forcing term at all, even a secant or a tangent, with no lucky guess required. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.